I am Mandy Askins. I'm the Assistant Collections Manager for the Cincinnati Observatory. So day to day, I manage the observatory's collections. Um, I curate exhibits, and I also do historical programming, like things like this today. So tonight, we're going to talk a little bit about um, early physical space exploration and Ohio's kind of role in that kind of physical space exploration. And again, we're only here for, half an hour, 45 minutes or so. So I'm really only going to focus on two specific places, the Cincinnati Observatory and one of our director's roles in a couple of NASA projects and other things, as well as Mound Laboratory, which is from, it's a south suburb of Dayton, Ohio. So it was actually the nation's first post-war World War II Atomic Energy Commission site, a Department of Energy site, and I'll give a little bit more background and history on that facility. Again, I could probably give an entire seminar or a whole semester's worth of content on just Ohio's role in space exploration and other things. Obviously, Ohio in general, when it comes to aviation and innovation, we are, up there when it comes to inventions and such. By the turn of the century, especially Dayton, Ohio, and Ohio in general had more inventions per capita than any other city in the entire world. So really only beat out by Silicon Valley much years later. So we have a lot of innovation, and that's kind of like in our blood and all of that. So we're going to talk about the race to space. So next year, we'll be opening an exhibit about the ending of World War II, the 80th anniversary of that, as well as kind of the birth of the atomic age. And the birth of the atomic age, we know that kind of culminated or not really culminated, began with the droppings of the atomic bombs on Hiroshima and Nagasaki. But really beyond that, when we later on look at Eisenhower's Atoms to Peace speech and the civilian applications for space, for nuclear energy, it really propelled the United States further in the space race, which kind of really put us on this forefront. And we'll talk about why Ohio is really important in all of that. So I'll give a little background. I'm sure a lot of us, especially if you're here listening to this talk, you've heard of Sputnik 1, you've heard of Explorer 1. Sputnik 1, was the first artificial satellite launched in 1957. Russia beat us to that and very quickly launched Sputnik 2. The US's response was Explorer 1, or the Explorer program. So I guess a question, even though I cannot, we can get to it towards the end because I can't see your faces or the chat while I'm in here, but maybe like keep in the back of your brain, what was the actual first space flight? And I'm going to answer it for you and we can talk about it later. It's easier when I give these presentations in person because I can ask the audience, do you know what was the actual first space flight? Well, it was the German V2 rocket on June 20th, 1944. So it actually, what we call the Kármán line, it reached that part of space. So much prior, obviously, than 1957, but really mankind was looking really early on. We think about astronomy and we think about space exploration, and both of those are really synonymous. You can't have one without the other. The observatory is obviously dedicated to public education about astronomy and space exploration, and our own history really has kind of like those roots in early physical space exploration. We currently, we use our Mitchell telescope, which is from 1843. We use that regularly. Many generations, 8+ generations of Cincinnatians have viewed that telescope. So that's our kind of gateway to the stars. But at the same time, when we look at physical, when are we going to actually start to send things out into space? And really by the 1920s, there were experimental rocket programs, power rockets, as we say, powering things such as planes, trains, and automobiles. And then obviously we know that the V2 German rocket was sent out in 1944. But by 1957, the Soviets had reached space prior to the United States. And in 1955, the United States announced that they would launch artificial satellites for the International Geophysical Year, which only led the Soviets to say that they would be launching one in the near future. So we know that they obviously launched one, and then they launched Sputnik 2, and then we got Explorer 1 into space. Thus started the Cold War, and thus started the race to space in 1957 and 1958. So we'll talk a little bit here. So Dr. Paul Herget was a director at the Cincinnati Observatory from 1943 until 1978. He was actually our last director as a research institution. We were and we are still a subsidiary of the University of Cincinnati, but in 1978, all research operations stopped and we became a nonprofit kind of dedicated to astronomy education, and now museum work and all of those kinds of things. Dr. Herget was responsible for computing trajectories and orbits and the development of the Atlas Intercontinental Ballistic Missile, the Vanguard satellite program, and the Mercury manned space flights. In his 1948 book, The Computation of Orbits, it was a landmark work really in the early days of the space program. And it's still currently today a required reading in celestial mechanics in graduate level programs. He taught astronomy at the University of Cincinnati, and he was a pioneer in the use of machine methods and eventually digital computers in the solving of like scientific and specifically astronomical problems. So if you've ever been to the Cincinnati Observatory, we have one room. Sometimes we call it our West Wing, but it's a classroom off to our main rotunda. And that room at one point prior to Dr. Herget was filled with our Meridian telescope. But during his era, it was filled with IBM punch card machines. So just lots of IBM computers that could compute data and mathematical calculations at a really rapid rate for the day's standards. So he would use these computation of orbits. In 1947, he founded the Minor Planet Center at the Cincinnati Observatory. It was the first of its kind. And still today, it still exists just at the Smithsonian Astrophysical Observatory. But it's the official body for observing and reporting on minor planets, such as asteroids. So all those little things floating in space, and we're hoping that they don't collide with Earth, or they, we just have to keep track of them. All of those were reported to the observatory from 1947 until 1978. And we kept track of those and calculated all of their trajectories and all of those orbits. Massive amount of publications that are in our archives that kind of show all the locations of all of those places. He also, during World War II, he applied these same kind of talents, his computation of orbits, to the war effort, helping to locate U-boats by means of the application of spherical trigonometry, which I call modern day battleship. So if you think about the fact that there's a radio station and we can send signals off and we figure out this is the likely location of a U-boat, we can figure out where it might be. And this so-called submarine book that he produced with all these calculations resulted in 30% less Allied deaths during World War II. So we were able to kind of figure out where those are. So he was able to apply his theory of computation of orbits to quite a lot of things. He was also a consultant for the Manhattan Project. And then, let's see, what's our next one? In a response to the launching of Sputnik, the University of Cincinnati established its Institute for Space Sciences, and Herget was named as director. So here we have Project Vanguard. It's very tiny. Vanguard it's about 6 inches. So if you look at that there on the screen, the Vanguard TV3, it's only about 6 inches big. So it's this tiny little satellite that we sent out into space. And it became the second artificial satellite successfully placed in a low Earth orbit by the United States in March of 1958. It was the first solar powered satellite, and weighed only about 3.1 pounds. At that time, it was also described by then Soviet Premier Nikita Khrushchev as the grapefruit satellite. So we sent a little grapefruit into space. Dr. Herget also worked on Project Mercury. And this was the first human spaceflight program of the United States, running from 1958 through 1963. And its goal was to put a man into Earth orbit and return him safely, ideally before the Soviet Union, because obviously we're in the Cold War now, so we have to outdo the Soviet Union in every capacity. It was taken over by the U.S. From the U.S. Air Force by the newly created civilian space agency, NASA. And it conducted a total of 20 uncrewed developmental flights, some of them using animals, and 6 successful flights by astronauts. After the successful launch of Explorer 1 satellite in 1958, obviously this crewed spaceflight became the next goal. The Soviet Union put the first human cosmonaut into space not long after. Let's see here. So next we're going to talk about Mound Laboratory. This is kind of something that I really enjoy talking about. I used to be a director at a museum in Dayton, Ohio, called the Mound Cold War Discovery Center. And so I'm kind of merging 2 of my loves together in this talk. Mound Laboratory was the first permanent atomic energy commission site to be constructed after World War II in order to continue Dayton's work within the Manhattan Project. It was known as the Dayton Project. It was probably the most secretive aspect of the Manhattan Project. They processed a radioactive material known as polonium-210 that would be used in the initiators or the triggers for the first atomic bomb. So spread out all throughout Dayton in places such as the Bone Break Theological Seminary. There was what they called the Runnymede Playhouse, which was actually a private recreational facility in Oakwood, Ohio, converting just everyday spaces into radioactive nuclear laboratories to process polonium-210 for the initiators for the first bomb. So when we think of the Trinity test and we think of the 2 bombs that were dropped on Japan, both of those had Dayton built and produced and processed polonium-210 initiators in them. And then after the war, it was decided that the United States needed a kind of comprehensive one facility that could take over work from Los Alamos, where all of the kind of final assembly of all of these nuclear bombs were done, into one location. And as a Daytonian myself, I like to say that there's a tenacity of Daytonians saying, well, we're not going to move. We like it here. So they initially wanted to put all this work near Oak Ridge, Tennessee. If you know anything about the Manhattan Project, the 3 main sites of the Manhattan Project were Hanford, Washington, Los Alamos, New Mexico, and I just said it, Oak Ridge, Tennessee, and Dayton being the 4th but secretive aspect of that. But the scientists did not want to move. It was a facility that was ran by Monsanto Chemical Company. This is way before they get into agriculture. They actually had their very first central research department in Dayton, Ohio at this time. And their main job was to produce things. I mean, this Monsanto and the company that was prior to that also produced the first ever modern fire extinguisher as well. So they were doing quite a lot of things. But it opened up officially in 1948 as an integrated research and development production facility to support the U.S. nuclear weapons, energy, and space programs. Space programs obviously come a little bit later. And it's kind of hard to see if you see on your screen on the large picture here where you can kind of see all those buildings, you'll see 2 little square kind of buildings sticking out. Those are actually elevator shafts, and they go into an underground facility below that. And it's kind of hard to tell, but the back of this picture here, the land is sloped, and there are 2 tunnel entrances. And this is where a pointer in person really comes in handy. And these two tunnel entrances and the elevator shafts went into a facility that was 3 stories underground, 122,000 square feet. And the two tunnel entrances each had 3 bomb blast doors. So they were kind of curved to the point where if in case of an attack, there was a little bit more security as well. This facility, Mound Lab, was built very similar to an average military base. It had its own fire department, it had its own police department and medical unit, cafeteria. Obviously, as a nuclear facility, it also had its own waste disposal. It was near a rail line, which is where all the nuclear material was kind of moved on and off site. But the underground facility known as the technical building or the T building was where all of the initial project, the polonium work, was done. Everything else above ground, it was a total of 17 buildings, and it was built within a year and a half by 3,000 workers. The technical building itself could withstand, it was built to withstand at that time the kind of most detrimental conventional weapon at the time, which was a 2,000-pound jet-assisted semi-armored torpedo. So imagine that torpedo coming in to that facility there. It could withstand that. The walls itself were anywhere between 16 to 20 feet thick of reinforced concrete. Thousands and thousands of pounds of rebar and concrete. When this facility was built, there was an actual order to say that kind of all concrete production went towards this facility at that time in kind of the eastern seaboard. So there's no moving that building. Currently, Mound Laboratory closed in 2003 when all of its final space missions programs left. And there is now a museum there, which if you ever get a chance to go, I'm very proud of that museum. I spent 5 years on that project, and it's a really interesting facility and place. The only original building that's left is the technical building, which I always tease and say that it's kind of just part of the earth now because it's 122,000 square feet underground. So it's just always going to be there. But everyone knew that it was an atomic research facility. It was secretive in the fact of what specific work was being done. The kind of running joke among the original 300 workers there, and even later on, at its peak, in 1988 had 2,500 workers across 300 acres and over 300 buildings. So it really grew quite quickly. But the running joke was that they built screen doors for submarines. So you couldn't really talk about your work. It was a need to know. It was quite secretive in and of that. So polonium was the initial work. And then we have these two men here, Ken Jordan and John Burden. In 1953 is when President Eisenhower gives his infamous Atoms for Peace speech. So the idea that, yes, we can build bombs. This is I guess depending on how you look at it, a context of human might and human ingenuity of what we can build, but this has peaceful means, which unfortunately is a lot of applications for military inventions and technology that we use it for things like bombs and stuff first, and then we decide, oh, well, it also has really great civilian applications. So, later on, if you think about nuclear energy in and of itself, we now have things like carbon dating. So we can, as an archivist, it's important to date objects. We can use carbon dating because of the invention of the atomic bomb. We now have nuclear medicine. We can irradiate people's cancer because of that invention. So I try to think about the good side of it, even though it came out through unpeaceful means. But Ken Jordan and John Burden one day were sitting at the cafeteria in Mound Laboratory. So it was a facility where you would each work in your own respective buildings, but you didn't always know what everyone else was doing. So if you were at the cafeteria, you knew that I couldn't necessarily talk about my work or your work within reason. So one of them was working on, or had kind of the idea that they could take polonium-210 and convert it into usable electrical energy through a small steam engine. The idea of, well, we have solar power, which I guess this is kind of the easiest way to explain a nuclear battery. We have solar power, we have solar energy that converts to usable electrical energy through the heat of that solar power. A nuclear battery just does that by the heat from the decay of a nuclear material. So Ken Jordan really thought that he could convert that. So they got special kind of dispensation, and they were able to work together to produce and invent the radioisotope thermoelectric generator, or known as the nuclear battery, in 1954. In 1959, it was patented, and you can see the two men here with their tiny little nuclear battery. The only thing is that polonium-210 has a very short half-life, is a half-life of 138 days. So the reason why Mound was so big, the reason why we had to produce so much polonium to produce these initiators or triggers, because if you think of 138 days, if I have 10 atoms of polonium-210, in 138 days, I will have 5. In 138 days more, I have 2.5. It depletes very quickly. The large majority of nuclear material will decay into stable lead, but it's something that has to be replaced quite often. But it worked really well, which could be a whole other topic in and of itself for the initiators, because it produced enough neutrons, but it did not cause accidental fission, and it basically didn't make the bomb go off quicker than it should. So it worked for that capacity. But for a long-lasting nuclear battery, 130 days is very short-lived. Eventually, Mound gets into using plutonium-238. So 239 is what we have in our atomic bombs. We also use uranium, but currently we use plutonium-238 for the large majority of our atomic bombs. And then obviously now we have hydrogen bombs, which we boost with another material that Mound worked with later. They also built hydrogen bombs. 238 is non-fissile, so it's not going to create a bomb, but it does have a half-life of 87.7 years. So it's really a kind of a long-range, long-lasting material. So here you can see a photo from Mound Laboratory's plutonium processing building in 1973, and then also a self-illuminating sphere of plutonium-238, which it's amazing, and it's gorgeous to look at, but also quite scary, I think. So you can see him, he's wearing a respirator and all of the other materials. There's, polonium itself is an alpha emitter. If you know much or anything about nuclear decay, an alpha emitter, it cannot penetrate your skin. So it is quite harmful. Usually things with a shorter half-life have kind of more initial, like if you're going to ingest it, it's quite harmful. But plutonium-238 is a beta and gamma emitter. It needs a lot more protection. So right now he's inserting a fuel cell into that kind of cradle there, and it's completely lead lined. So it will shield that. It will actually stop the material from penetrating anything else further. So it's a way of kind of protection and all of that. One day I'll give a talk all just about that, and that will be quite interesting. But they realized that with plutonium, they with the Transit 4A satellite in 1961, Mound had been producing at that point kind of small scale nuclear batteries. We also call them SNAPs, or Systems for Nuclear Auxiliary Power. We know that the government really likes all of their acronyms, but and at this point in 1961, we're sending out small scale satellites, usually navigational satellites. These were the transit satellites were Navy navigational satellites. Prior to 1961, they were all solar powered, but the one in 1961, Transit 4A, they put a backup of a small scale nuclear battery, the SNAP 3 RTG, And the solar panels actually ended up all failing. And the RTG was able to pick up all of that power and power this satellite quite successfully. So it produced, this was the very first time that a nuclear heat source or a nuclear battery was ever launched into space. And then not long after, 2 Transit 5 satellites were launched into orbits, and all the sole power source were nuclear batteries or RTGs, which I'll use that term from now on, RTGs, because saying radioisotope thermoelectric generator multiple times in a row is kind of a mouthful. But the transit satellites ended up continuing. They produced quite a lot of them. And all of them after 1961, when that one was so successful, were all powered by Mound produced, which is right outside of Dayton, Ohio, in Miamisburg, RTGs. We also produced other satellites with RTGs, such as the Nimbus 3 and the Lincoln experimental satellites. So here you can kind of see the Transit 4A before it was launched. Obviously a lot bigger than some of the other ones that we had sent out. So then we have the Apollo missions. Here you actually see, here at the, I guess if you're looking at it, it's going to be on your right-hand side. That's from Apollo 12. That's Alan Bean removing the nuclear fuel capsule from outside of the lunar module, and he will be putting it in that apparatus that you see on the moon there. This was known as a SNAP 27. So again, Systems for Nuclear Auxiliary Power, Model 27 generator. The interesting part about these radioisotope heat sources, that there are no moving parts. Everything is produced through thermocouples and everything. There's no actual physical moving parts in these. Every time you see one, you'll see kind of these fins deflecting, because nuclear decay produces a lot of heat, and you do not want instrumentation and other things kind of overheating, or the fuel cell, the fuel cell and the components itself overheating. So it helps to deflect that heat. With Apollo 11, though, it was not a full-scale RTG. It was slightly larger than I guess a can, like, you know, if you think of a can of beans or something like that, it was only slightly larger than that. And it just only produced heat for the instrumentation packet, the ALSET package that we left on the moon, so that it would keep all the instrumentation warm during kind of cold lunar nights. But by Apollo 12, we were producing full-scale battery systems that would then power these instrumentation packages. You know, we have things like seismometers and other detectors and things that would send back information to Earth, so we could learn about the moon, moonquakes, and quite a lot of other things. And because they work so well. Obviously, with Apollo 11, our main goal was to get humans on the moon and then return them safely back. So the idea of adding something like a nuclear battery that we weren't quite sure how it would work was saved until Apollo 12, when we knew we could successfully bring humans back and forth from the moon. One interesting fact, we'll go back here to Alan Bean here. This photo here, and there's also photos from Mound Laboratory's collections where Alan came to the facility to kind of practice on using the tools in space and how to grab the fuel capsule and put it into the generator and everything. But here, if you ever want to go back and you're a space nerd like me, read the transcript of Alan Bean doing this, because right now in that photo, he's talking to NASA and he's telling them what's going on. And at one point, the fuel capsule gets stuck, and they didn't quite account for the full thermal expansion. So he took out a space hammer and hit the side of the fuel capsule to kind of dislodge it, and then pulls it out. And I can only imagine kind of I guess the ego you have to have just to, good or bad, to go to space. But you're on space and you're hitting a fuel capsule of plutonium-238 with a space hammer on the moon. And this is the first time any other human has ever done this, to dislodge it. And then he does it, and it's great, and it powers the ALSEP package, and it's great. But it's a really funny transcript if you ever want to go through and read those things. So here, and again, I wish I could see the chat when I have a full screen, but we'll talk about it at the end. And I'll ask everyone, kind of like, think in your brain, where do you think Apollo 13's RTG went? So we know that that was a failed mission, and we returned the astronauts back to Earth, but they were really worried about, where is this nuclear battery going to go? Because it's already been into space. We aren't sure if it's going to leak, if it's going to cause, any kind of human, going to cause anything bad. So they purposely launched it, removed it as the shuttle's coming down, as the vehicle is entering space orbit. They throw it out. But think about, where did we land it? And then we'll get back at the end to the chat, because it's a very interesting place where they put that. So if we think about why am I talking about Dr. Herget, who worked on these space satellites, and other programs like Mercury and all this, and then why are we talking about this laboratory that was outside of Dayton that produced triggers for bombs, but also batteries for space? And I think it's significant because I could sit here and I could talk about GE Aviation. A lot of us that are live in and around Cincinnati, we know that GE Aviation had quite a lot of roles, especially through World War II and other things. At one point they thought they could put a nuclear reactor on an aircraft. They had a lot of roles. We also have NASA Plumbrook up near Sandusky, and the list kind of could go on with all of these applications. Well, I really feel that the invention of the nuclear battery in 1954 really opened mankind's actual physical, we could physically get to space, but beyond the sun's solar energy, we cannot really send anything beyond that. Currently the only spacecraft that is past sun solar energy is Juno. We have obviously Pioneer 10 and 11 here that was launched in 1972 and 73. And you can kind of see here, if you see those kind of two arms that are really far out, and you'll see those little RTGs with their little fins. Those themselves have 4 SNAP 19 RTGs as its sole power source. Pioneer's its mission was to study the outer planets such as Jupiter and Saturn and the heliosphere. So beyond the sun solar energy, our really only way to explore space physically, even with the spacecraft, and maybe hopefully few humans in the future, is through nuclear power. That's currently the only application that we have. So this invention, I don't like to say that the United States won or lost, like anyone won or lost the Cold War or the space race. Typically, as historians, we say it wasn't a physical war, so nobody actually really won or lost. But this pushed the United States further into that space race. But it also really propelled mankind into the idea of that we can achieve and reach the farthest reaches of space. We have Viking 1 and 2, which launched in 1975, which was a mission to Mars. And each lander had 2 RTGs on them. And then we have Voyager 1 and 2, which is probably my favorite spacecraft to talk about. They launched in 1977. They are the furthest objects that mankind has ever sent out into space. And when I updated this program, because I've given various kind of presentations of this over many years, I had to update it. It was at 9 to 11 billion miles away, and I had to update it to 12 to 15 billion miles away. So it keeps going. We can still communicate with Voyager 1 and 2. The RTGs are continuously working. And when we think of the kind of the birth, or like the initial life of the battery, we indicate that it should be around 87-ish years. The effects of space and radiation can be quite detrimental on a lot of the instrumentation, not necessarily the battery itself. So the further we go out, so there are parts of Voyager 1 and 2 where instruments no longer work, but we can communicate with them. It takes anywhere between 20 to 30 hours for us to initiate contact and then for these spacecraft to send us data back. So I think that, you know, if any of you really love Carl Sagan and the idea of, you know, that kind of the family portrait, you know, when Voyager turns and looks back and then Earth is this tiny pale blue dot. So this was a significant invention, I think, in mankind's physical space exploration. So here's a picture of a model called the multi-100 watt. And if any of you are Doctor Who fans, I think I've always thought these looked like Daleks. So this is much better when I'm given it physically in person because people usually laugh at this point. But and here's another kind of breakout model of the general purpose heat source. So it's a larger model. It stands about 4 feet tall. So if you ever go to the Mound Laboratory Museum, there are models of every Mound produced RTG in that museum. So up until 2003, Mound Laboratory outside of Dayton produced every single RTG for space missions. They designed, they tested, they had a plutonium processing building, and currently all that work is done at Idaho National Laboratory. So you can kind of see it there, but no moving parts. It's just in theory nuclear material and thermocouples and cooling tubes and things like that. So if you think of beginning of life, typically it could produce around 300 watts of thermal energy, and the excess heat. So if you think about heat and the deflection, 4,500 watts or so of heat that was produced. So we have Galileo in 1989. That was launched to study Jupiter and its moons, and it had 2 RTGs as its sole power source. Then we have Ulysses in 1990. The goal was to study and orbit the sun and study its latitudes, and it had one of those larger 4 feet long, 4 feet tall general purpose heat sources on it as its sole power source. Then we have Cassini, which unfortunately we had to, part of its goal was to crash land into Saturn. So we were able to see and image kind of the inner rings of Saturn. So this mission was quite successful. So if you ever get a chance to visit the observatory, currently now we, I guess between now and fall, it's like perfect Saturn viewing season. I got to see Saturn the other day. So, you know, you can kind of think about how much we've learned about Saturn and these further outer planets due to some of these spacecraft, which are powered by these batteries invented here in Ohio. So Cassini had 3 of those much larger batteries as its sole power source. In 2003, Mound closed. It was kind of part of a reorganization of the Department of Energy. And Mound was also, you know, initially it was built in a very rural area, but the city in Miamisburg itself grew up really close to the laboratory. And that was also the time of clean energy and people really being concerned living so close, rightfully so close to a weapons complex. So the site closed officially in 2003. And which the last missions to leave were the Space Nuclear Power Systems program. They had 1 leftover RTG that they sent off to Idaho, which is now where all of that work is done. And that last RTG, Ohio-produced RTG, is on New Horizons, which was launched in 2006 to study Pluto and explore the Kuiper Belt. So it was the last RTG there. And today, we have what they call multi-mission RTGs. So the idea is that they can be reused. So things like Curiosity, that rover has a multi-mission RTG on it as well. And like a lot of technology, everything gets smaller. And we're producing what we call next-gen RTGs. And the goal is for them to be flight ready and based on the designs of the larger scale general purpose ones by 2030. The United States started to produce plutonium again in 2016 during the, I guess the late 80s to mid 90s and even later, kind of right at the end of the Cold War, we were actually buying our plutonium from Russia, which is a whole separate interesting topic. But we were actually buying that material because our reactors were just unable to kind of keep up with that and stuff. But this RTG work continues at Idaho National Laboratory at once Mound closed in 2003. So currently though, let's see here. Kind of talk about the Artemis and other missions. The goal for the Department of Energy and NASA is to continue to produce on average a goal of 1.5 kilograms of the isotope plutonium-238, and they're expected to reach that goal by 2026. So next we're going to talk a little bit about the Artemis mission. I know I'm kind of pushing my time a little bit. And this is why we're really excited about it, because next year we're going to open an exhibit talking about this kind of early exploration of physical space, and Ohio's role and the observatory's role. But, you know, we know we've launched Artemis 1, and Artemis 2 is planned to be launched next fall, which will be the first crewed test flight of the Space Launch System and the Orion spacecraft. There'll be 4 crew members, which includes I believe it's the first woman and the first person of color. Eventually with Artemis 3 will land on the moon. And the interesting thing about Artemis is when we land on the moon, the goal is to have these RTGs, these next gen RTGs, power a moon base. They are planned to use plutonium-238, but there's also currently a lot of ideas about using depleted nuclear materials such as strontium-90 to power like kind of small scale batteries for other things like that. So, and Artemis 3 is planned to be launched in 2026, which will be our first moon landing since Apollo 17 in 1972. So, I really hope that you guys, you know, kind of think about I guess the goal of this talk is to think about the large scale significance of this one invention of these 2 men that sat down at a cafeteria that, you know, maybe not everybody likes Monsanto now, but that time they were a really great employer and they really propelled innovation and paid for these things. They sat down and thought, well, how do we take this material and produce a long-lasting battery? And I don't think that even these men really would think now it's being used to create a moon base or send the furthest object, you know, into space, Voyager 1 and 2, that mankind has ever done. So this small invention is really our access and our ability to ever physically discover space on a significant level. So, but yeah, really, that is all I have. Let me stop sharing, and hopefully that worked out.
Thank you, Mandy. That was really interesting.
Cool. Anybody have any questions? Oh, so the question was, where do you think Apollo 13's RTG is? Anybody? No? Where do we throw it? We threw it out. We threw it out. Where do we think it is?
It didn't burn up on re-entry?
No, it did not. It was safely inside the module. And then once it hit into Earth's atmosphere, they actually purposely shoved it out into a specific place. Anybody can guess? Mostly to protect it. So water is a really good moderator of nuclear material and heat. So we think of nuclear reactors. They actually threw it down so it would land at the bottom of the Tonga Trench, which is in the South Pacific. So
yeah, I would not have guessed that.
And we actually have quite a lot of space junk
Hmm.
in the Tonga Trench as well. But we've sent, other things down there to kind of check on it, and it's, it's covered with barnacles and, all these other things. But it's still emitting heat. The battery itself is still decaying, but it's safely kind of away from humankind. But it's at the bottom of the Tonga Trench in the South Pacific. So that's just if one day if you're ever at trivia and you're like, I know that, thanks to Mandy, but there you go.